Hello and welcome back everyone to the penultimate installment of our series about the analysis of N-of-1 trials. Last time we built a Bayesian model to handle a continuous variable. This time we will be dealing with categorical variables as predictors in our model. So remember last time we had a model for age or for height better among the some people. However, among these people, there are about slightly under half are males and slightly over half are females. And obviously, males and females do not have the same body height. This is true for all humans, also for the SAM people. So we need to adapt our model a little bit and get a separate estimate of the mean height for males and a separate estimate of the mean height for females. So how do we do this? Well, we can still start from the same model where we say that height for each group, this is HI in this case, is a normally distributed variable with some mean and some standard deviation. So here nothing much has changed except that we're going to do or determine the height for two separate groups. Our model has been adjusted a little bit where we have a intercept and the parameter or the multiplication factor or the weight for gender, for maleness in this case. So we assume that the average, the overall average, is still similar to the prior that we've done before, which is basically saying, okay, this is 178 centimeters with a standard deviation of 20. And now for the males, so male is indicated as a 1 by the male variable. We assume that they have on average a similar height to the females, so that there's no difference, and a standard deviation of 10. For the sigma, we again view a uniform prior where all values between 0 and 50 for the standard deviation are equally likely. So what does this look like if we put it into, if we start plotting these priors? So first we will do this for the females where nothing really has changed, and for the males we've added, so this is just the A term because the beta value, this value times 0, together this becomes 0. And for the males we've got A plus this beta, which is a normally distributed variable with a mean 0 and a standard deviation of 10, times male, which is 1, so only this. And I've put this into the code here. Now let's compare these priors. So first for the females, which we see over here, and then for the males, which we see in the dotted line. Now if we zoom in, we can immediately appreciate that although the mean is similar for both, we see that the variation for the males, if we formulate our prior this way, is slightly bigger. So it's a slightly flatter and slightly wider distribution. Now, this is not realistic, right? Why would the variation for males and females be different in heights? We only believe that the mean for males and females would be different, not the variation would be that the variation would be different. If we formulate our priors this way by creating a separate normal distribution for males and females, then we run into this trouble where if we add the distributions or the normal distributions, that error always adds up. So variation always increases if you start adding error. So what we want to do instead is to have a indicator value, which is saying, okay, and we will call this indicator sex. And if we create sex, then we have a if male were to be 1, then we give the value 2, and for everything else we give it a value 1. I've plotted the content of this new numeric vector, and so this is a male, female, female, male, and we can have this indicator in our model. Our model becomes slightly different then. So instead of having this added prior for males, we can have the combined prior in one, where it's still the height for males and females. It has some value mu for the mean and a sigma for the standard deviation, and the mu as a alpha, or a separate estimate for sex for each element, and each element is in this case 1 for the females and 2 for the males. And here we see that this is a similar distribution actually for males and females, and the sigma again is similar. And we can again use the quadratic approximation like we did before. So let's run this model. You see we're still using the Howell data for this. We can show the model summary, and here we see that for A is 1, which is females, the mean height would be 150, and the for the males the mean height would be close to 160 with standard deviation of 0.5. We can again sample the posterior, and the nice thing now is that we can also calculate the difference in means from this posterior. So post A1, that's the column for representing the females, and post A2 is a column representing the males. I could just show you the contents, or at least some of it. So these are the first 6 average heights for the females in the posterior distribution. And these are the first 6 average heights for the males in the distribution. And we can just subtract these numbers. And I'll also show you the difference, and we can compare this. So if we subtract, if we do this 149 minus 160 and a bit, we get a 10-point difference. And you can check these numbers yourself to see if this actually makes, if these subtraction actually makes sense. So basically what we do is we just subtract the first column, the second column from the first, to get the difference for all of the values in the posterior. And so we can see that the average difference in height is actually 10 centimeters. So the women are 10 centimeters and a bit shorter than the men. And this is the way that you can compare the posterior distributions or the posterior means. With this, we have all the tools we need to answer our questions and analyze our N of 1 data. And in the final video, we're going to bring all of what we've learned together and analyze our N of 1 data. So thank you for your attention, and see you next time.